Here's the last thing in uh, chapter 4, section 5, dealing with applications and models. And so here's some applications of how to solve logarithm equations and exponential equations. So here's kind of an interesting one. It takes time to create a habit, and however many times you create a habit, then you get then the longer you do it for, more times you do it, the stronger that habit becomes, right? So here, psychologist CL Hole came up with this formula. If you want to find H, your strength of a habit, you have this equation: 1,000 times the quantity 1 minus E raised to the k times n, where n is the number of times of repetition, and k is our constant. And so we'll find k. Now k will not be an actual number, but if you plug in an n and an h, then you can find k, and then you can use that in order to find other values for h or n. So this is pretty interesting, because if we go ahead and just solve for k, which they want us to do, we can solve for that constant variation. So we take this equation, and we want to get this k by itself, or this k by itself right here, and a positive k. So first of all, we need to get this base e by itself first, right? So we're going to divide by 1,000 on both sides. So we have h over 1,000 is equal to 1 minus e to the minus kn. N is the number of repetitions. And so now I'm just going to go ahead and add e to the left side, and then subtract the h over 100, or over 1,000, sorry. And so I get e to the k times n, the negative k times n, equals 1 minus h over 1,000. And now we want to get that exponent, right? In order to get to the exponent, we have to take the log of both sides, and since our base is e, we want to take the natural log of both sides. So I'm going to take the natural log of this, and then I'm taking the log of 1 minus h over 1,000. Okay, and now I can go ahead and bring down my exponents, and then it is ln of e, and remember ln of e is equal to 1. So this is minus k times n equals ln of the quantity 1 minus h over 1,000. Now here I'm going to divide by a negative n, so I can take that negative away, so I'll divide by negative n on both sides. And so then k would equal ln of 1 minus h over 1,000 all over negative n. Okay, so there's k. Now we can solve for k. So now we can go ahead and find that constant if we want to. Right, we can plug in an h, how strong we want our habit to be, and then n, how many times we want to do repetitions, right? And we can find that constant of the variation. Probably the larger the n you have, and based on what n and h is, right, k is going to change, right? So if you only want to do one repetition, and you want your strength to be, I'm not sure if the strength is in a decimal form, or kind of what's the highest strength, maybe 100, so I don't quite know what the number of units is for h, but if you put in, you want a strong habit, whatever that number might be for h, and you only want the least amount of times, that means your k is probably going to be something that maybe really, really small decimal, or maybe really, really big, right? But if you had a large amount of n's and then a relatively high h, then your k is going to be totally different, right? So you could use this formula. I'm just not sure what kind of a high h would be. So basically you're just kind of reworking these formulas to solve for a variable, and that's like number 85 that you're going to do on your homework. So you're just rearranging these and solving for a different variable. Okay, so here we go. We have a table. It's not shown on here. It's in the book, but it gives coal consumption, and it's modeled by f of t is 24.92 ln of t minus 93.31, where t has to be greater than or equal to 80, and t represents the number of years after 1900, and f of t is in our quads, or the British thermal units. So what they're asking for here is we want to find approximately what amount of coal was consumed in the United States in 2003. So we want to find out, okay, in 2003, how much coal was consumed, and how does this figure compare to the actual number of 22.32? So in 2003, the actual number is 22.32. And so we're going to use this formula. We're going to plug in our t here, and t is the number of years after 1900. So how far is 2003 after 1900? Well, that's 103 years, right? So we're going to plug that in. So 24.92 ln, parentheses will come up, plug in our 103, close that parentheses, and then minus 93.31. And so now we can go ahead and plug that in, and we get approximately f of 103 is 22.19. So that's what approximately it is. So it's pretty close. So this formula is pretty close there. And then they kind of want to, if the trend continues, will the annual consumption reach 25? So when will it reach 25? So we want to find when will the f of t equal 25, right? So when will this equation (93.92) no, 31. When will this reach 25? So we're solving for t here. So we can add 93.31 to both sides. And so then we get 118.31 divided by 24.92. So now we have ln t by itself. And why I don't actually divide this is because I want this number to stay true in my calculator. I don't want to round that answer. Okay? I don't need parentheses there. Okay, so now I want to solve this for t. So it's an ln. It's a log, so I need to switch to exponential. So the base is e. So e raised to this 118.31 over 24.92. Close that parenthesis, so I could really do that in my calculator. Hit the e button, this parenthesis will come up. I type in this top number, I hit divided by, right in the bottom number, close that parenthesis, and that will give me my t. And so t is approximately 115.3 years. So that's how many, so that's 2015, right? So approximately 2015, it should, if it continues in this trend, would reach 25 quads, or British thermal units of coal consumption. Okay? And this is like number 105 in your homework that I'm about to do right now. Okay, so on page 448, you have number 85 and 105, and I'll go ahead and do those right now. Okay, so here's number 85. Here you're given some type of equation. I don't even know what it represents, and it doesn't really matter what it represents, but you're going to be solving for t. Okay, so you're just going to manipulate this formula in order to solve for t, right? That's what they do a lot. You have different, I mean, you have different formulas like speed is distance over time, where you can solve that equation for time, right? So we're just taking this equation, whatever it represents, and we're going to go ahead and solve for t. So we're trying to get t by itself. So in order to get to my exponent, I first need to get the base by itself, right? So it means I need to get rid of this. So how do I get rid of multiplying by e over r? Well, I either divide by e over r, which is the same thing as multiplying by r over e, because remember when I multiply, that I can cross cancel, right? So that means this side has to be multiplied by r over e. So I got to do it to both sides. So this is ri, because I is in the numerator, right? Ri over e equals 1 minus e to the negative rt divided by 2. Okay, now I can go ahead and add my e with the base and then subtract this ri over e. I'm just rearranging these, right? So I have a positive base. Or I could subtract 1 on both sides and then multiply by a negative. Okay, so I want to move this e over, so then it is positive e. And it's going to be 1 minus ri over e. Okay, now I need to get to this exponent. In order to get to that exponent, I need to log both sides, and since I have a base of e, I want to ln of both sides, right? I'll go ahead and just rewrite it. So I want to ln both sides. So ln of 1 minus ri over e. Right, and now I can bring this out front, and then that ln of e is going to equal 1. This is rt divided by 2. ln of 1 minus ri over e. Then I can go ahead and I'm dividing by 2, so we'll multiply by 2, right? On both sides. And ln of e equals 1. So multiply by 2 on both sides. And then we can divide by negative r. So t is equal to 2 ln of 1 minus ri over e all over negative r. Or you could write it like this: 2 over negative r, or negative 2 over r ln of 1 minus ri over e. Those are both the same. Okay. Alright, so there is number 85. Now we can just do 105. Number 105. And this is where we're kind of using the table, or like our example. This one, it gives us a formula for CO2 emissions. And that formula is ln of 1 minus p equals negative 0.0034 minus 0053 t, and that is a capital T, so I'm pretty sure that's probably a tax or something like that, because it's emissions tax. So if we read this, this is the equation for the cost benefit equation. So this is relating to the CO2 emissions tax, so you get taxed. And this tax is based on the amount of carbon dioxide emitted into the air when the fuel is burned. Okay, and so what we want to do is we don't have a graphing calculator, so we can't do B, but A is asking us to write P as a function of T. So that means that we want to rewrite in terms of P alone. Okay, so that means we need to solve for P, and our variable is going to be T. So we want to get P by itself. So we're going to rewrite this equation. I cannot distribute that ln, right? So that means I need to switch this to an exponential first. So this is base e, right? Ln is log base e. So e raised to my answer, negative 0.0034 minus 0.0053 t equals 1 minus p. Now I can go ahead and just add p and subtract the e, right? So p is equal to 1 minus e raised to the negative 0.0034 minus 0.0053 t. So p is solved for, and what they mean in terms of t is just like our f of x equations. You have a function f, right? but it's in terms of x, meaning there's an x in the variable. So this is P of t. I can write it like that because my equation is for P, but it's in terms, meaning the variable is t. Okay. So there we go. So there is A. Now B asks us to discuss the benefits of continuing to raise taxes on the carbon if our T is between 0 and 1,000, and T is the dollars per ton of carbon, and P is the corresponding percentage reduction in decimal forms of our emissions of carbon dioxide. So we want to determine P when T is 60. So we're going to plug in 60 in for T here. So we plug in 60 in for this T, so P of 60 minus 0.0053 times 60. Okay, so here we can enter this kind of in our calculator, and we just want to, it's going to do it, just make sure that we put parentheses, so you can just type 1 minus E and then it'll do parenthesis, right? You can do negative 0.0034 minus 0.0053 and then just parenthesis 60 and then close this E off, and that will give us our answer of approximately 0.275. So our P of 60 is 0.275 or 27.5%. And then it asks us, okay, what value of T will give a 50% reduction in carbon emissions? So if we had a $60, this one is saying, with P of 60 is saying that if we had a if we had a tax of $60 per ton of carbon, then we would have a 27.5% of reduction in carbon emissions, carbon dioxide emissions. Okay. So if they want to reduce that even more, right? If they want to reduce that instead of 27.5%, they want to reduce the carbon to 50%. What would they need to do for a tax? How much would they need a tax per ton of carbon in order to have that reduction of 50%? So if we want our reduction to be 50%, just 0.5, right? 0.5, then what would this T need to be? What would that T need to be there? Now we could really go back to this original problem with the ln of 1 minus Rp, which is now 0.5, equals e to the negative 0.0034 minus 0.0053t, and go ahead and solve this for t, right? So we need to get this exponent by itself. And we could enter it in right here as well, right? I'm gonna need to add 1, and that's what I do, right? Or subtract 1, and then I switch my e's and stuff like that to a positive e, and that's where it kind of gets switched around here. And then we can go ahead and take the ln of both sides, and we get this. And messed up here, this actually doesn't even have an e there, it's just that, as you can see. So then all we have to do here is just take this and divide, or I can't divide yet, so I gotta actually add 0.0034 to this, add 0.0034, so I have ln of 1 minus 0.5, which you can simplify that, right, plus 0.0034 equals negative 0.0053t. So now we can divide by negative 0.0053. So we have ln of 0.5, right, because 1 minus 0.5 is just 0.5, so a half, ln of a half, plus 0.0034, and then after we do that, then we're going to divide. So I got to take the ln of 0.5 first, put that in your calculator, close that off. So basically you can, if you put that in your numerator, those parentheses, and then you divide by negative 0.0053, we'll get our t which is approximately a tax per ton of carbon. In order to reduce our emissions by 50%, needs to be $130.14. So that's what they need to charge per ton in order to get a 50% reduction. Okay, so that's it for section 5.